Ladies and gentlemen, welcome to this distinguished lecture series organized by the Poly Academy for Interdisciplinary Research, or PAIR. So as you already seen from the video, PAIR conduct research in sustainable cities, advanced technologies, and health and well-being. And PAIR organize this lecture series at least once every month. We invite outstanding scholars, also the administrators from universities and then the industry to give us the state of the art on their respective field. And today we are very happy to have a Professor Ioannis BRILAKis. Sorry for mispronounce of the name, from the Cambridge University, so who has done outstanding research on the built environment. And I'm so pleased to see that we have more than 700 registrations through online and on-site. And now I would like to invite our Vice President for Research and Innovation, Professor Chris CHAO, to give an opening remark. Thank you.
Thank you, Ian. Good afternoon, ladies and gentlemen. It is my great pleasure to introduce our distinguished speaker today, Professor Ioannis BRILAKis from the University of Cambridge. Professor BRILAKis is the Lung O Rock Professor of Civil and Information Engineering and the Director of the Construction Information Technology (CIT) Laboratory at Cambridge University. His works focus on automation and information technologies in the construction area. These cover building and infrastructure digital twins, infrastructure computer vision, and pattern recognition, technologies for communication, collaboration, and coordination, etc. All are very important areas in the modern construction area. Today, Professor BRILAKis will enlighten us on digital twinning. This technology uses real-world data and machine learning algorithms to create simulations. Digital twinning helps optimize the construction process. It enables the visualizations of the environment so that before construction begins, engineers and builders can already identify the bottlenecks and make optimization for physical assets and processes around it, for example, like energy systems, maintenance, and facility management. At the Construction Information Technology Lab, Professor BRILAKis and his team work on multidisciplinary research, education, and technology transfer in the field of built environment. Among the projects, the Digital Roads of the Future initiative is a £14.5 million program in which Cambridge University collaborates with National Highways, Costing Group, and other industry partners in the UK to build a connected physical and digital road infrastructure system. Through the use of digital twins, smart materials, data science, and robotic monitoring. Professor BRILAKis' contribution to construction automation and robotics is widely recognized. He has published over 200 papers in peer-reviewed journals and conference proceedings. He is the editor for several journals published by the American Society of Civil Engineers and Elsevier. He received the National Science Foundation Career Award and multiple awards from the European Council on Computing in Construction, the American Society of Civil Engineers, and Georgia Tech in recognition of his research and outstanding service in the field. Professor BRILAKis obtained his PhD in civil engineering from the University of Illinois in the US. Before moving to the UK, he served in the University of Michigan and Georgia Institute of Technology, Professor BRILAKIS has visiting appointments at other universities in the US, Australia, China, and Germany. He is the lead founder of the European Council on Computing in Construction, a professional society dedicated to information technology for construction engineering and management. So without further ado, ladies and gentlemen, please join me in welcoming our distinguished speakers, Professor Ioannis BRILAKIS, today. Thank you.
Thank you very much for coming today. And thank you, Professor CHAO and CHEN, for the introduction. And many thanks to the organizing team for all the hard work to make this lecture possible. I'm Ioannis BRILAKIS. I work for the University of Cambridge, and I'm here to talk to you about digital twins, and specifically for the built environment. Before I do that, a few things about the place I work at. I don't know how many of you have been to the University of Cambridge. It's a really nice place, very touristic location, in fact. I have some pictures here from, I think it's Corpus Christi, King's, and Trinity. The university was established in 1209 by King Henry III. We celebrated our 800th anniversary about 10 years ago. And since then, we've had a number of very notable alumni, eminent mathematicians, scholars, and other academics, some of which you might see in this picture. You might recognize Isaac Newton, Niels Bohr, Alan Turing, John Harvard, who established Harvard University later on, John Maynard Keynes, our recently departed Stephen Hawking, and many other people that you probably recognize from TV and other places. I won't mention those. I happen to work in a place that could easily look like it was a place here or any other place in the world called the Civil Engineering Building. You can see how architecture is converging around the world. Every building looks the same, right? This could be anywhere. So that's not what's special. What's special is what happens inside. And what we do inside there is we focus on how we can leverage digital twins to achieve the digital transformation of the construction industry. And why are we doing that? It's all about information management. We know that better information management will help us do better on everything. Better in terms of cost, time, quality, safety, sustainability, every single factor. Information management can unlock that. Digital twins have the potential to offer us that better information management, but it's still a potential. And if I was to ask each and every one of you to give me a definition, I will probably get a slightly different definition from everyone. So I've done a lot of work trying to dig into that and understand what it is that we mean by digital twins and how can we exactly apply it and get value out of it in this sector. So let's start with a definition. And I'll go into something super basic. Imagine you're a 1-year-old and you're learning how to walk. And you take a step forward, it's the wrong step, so you fall down, right? You took an action, it was the wrong action, you fell down. 2 signals come to your brain. First, pain. It's painful to fall down. Second, actually, I didn't get where I wanted. So you take that data into your head, you process it into knowledge. The knowledge is, I failed in my objective. And you start doing projections, simulations. What might I do next time? Should I put my foot here, there, there? What would be the best scenario that will most likely yield me the correct location? I make my hypothesis and then I act upon it once again and continue that loop. This is the loop between the brain and the body. And we do that on everything. And it happens so subconsciously that it's automatic. That's possible for really simple tasks like walking, playing football, or other things. Not so much possible for something that's very complex, like managing infrastructure. So what we do with computers is we effectively outsource part of our brain and put that in a computer to allow us to make that loop possible with more computing power. So this is what I call the engineering sequence that comes out of that. You have your body on the left, the physical asset. You have your planned asset on the right, also known as the brain, more specifically the prefrontal cortex, what boys don't have until the age of 25. And within that space, we monitor the physical asset, produce data, we interpret that into knowledge, we use that to run forecasting and forensics, go back in time and forward in time, make decisions, and then act upon those decisions in the real world. I haven't told you anything new. You already know this. So the first bit that's new is that in that space, the digital twin is the bit on the right. The physical twin is the bit on the left. And the combination of all of this is the twin system. So we're here really talking about twin systems, not necessarily digital twins, but the combination, how that thing works together. Why do we need twin systems? Why do we need digital twins? Well, we want to increase automation to manage increasing asset complexity. We want to combine product and process. We want to combine modeling, simulation, and monitoring all in the same place. And as a result, we can end up with something that's quite complex and expensive to design, to construct, to maintain, and operate, but also very rich, therefore very valuable and flexible, able to serve multiple purposes. We're also now into a world where we can no longer keep all the data in one place. We have to work with federated systems. We have to connect different systems together to get the most value out of them. And we have to make sure that they are extensible and future-proofed. The example I like to use is Thames Tideway in the UK. It's a huge concrete pipe that's meant to last for 200 years. And I was discussing with colleagues who wanted to embed sensors in the concrete. And I said, are you serious? The sensor is going to last 5 years, maybe 10. What are you going to do the other 190 years? Right? We have to understand that we are working in a system where our assets last for very long, and we need to be able to maintain them for a very long period of time. The value of digital twins: better decisions, faster refresh rate, more trust in the information, the ability to solve multiple processes, and more automation, leaving the high-level decisions to humans, but taking on absorbing the low-level decisions and being able to do them directly from the digital twin. The best example of the latter is autonomous driving. Autonomous driving is full of low-level decisions, and it's the reason why it's possible, why we can create the entire twin system loop inside the car. So, if digital twins are so amazing, then why aren't they as ubiquitous as physical twins? Well, the answer is we know the physical twin as a product and processes, but we're still discovering the digital twin as a product and processes, and we need to do a lot of research in that space. The owners also understand the value of physical twins, but not so much the value of digital twins, because they haven't quite seen what it can do. And we need real use cases to drive rapid market penetration. And last but not least, vendors tend to present incremental solutions as groundbreaking, relabeling existing products into digital twins, and therefore accelerating digital twins into the trough of disillusionment. How do we solve that? Well, I started, first of all, working with colleagues. This is a paper with a colleague from Technion, Professor Raphael Sachs, to try to understand what is the potential. What should be the 20-year target? And this is one of the figures from that paper where we looked at the example of, think of a human standing in front of a lake. The human is the physical asset. The reflection is the digital asset. That's what you see here. The vertical axis is physical product and process. The negative side is information volume. And you can see that at the beginning of the life cycle, we start design. And while we're designing, we're producing design, product, and process information. And this is what we call the design phase digital twin, or the unborn digital twin. Then you hit birth, and that's when we start constructing the real asset. Notice that up to this point, there is a twin, the digital twin, and it comes first, before the physical twin. So at birth, we have construction processes, prefabricated materials come alive. Later on, at the weaning phase, we leave the mothership, we go on site, and we start constructing an asset from nothing into a mature adult asset. That's the child growing process. And at the same time, we're producing construction product and process information, which goes into that construction phase digital twin. And later on, so on and so on, in the operation phase, we have our operation adult physical twin with operation processes producing operation product and process information. This figure is not unlike humans and our brains, to go back to the previous example. Just like humans, we are born, we grow up, we degrade over time, like the physical assets degrades over time, but the wisdom grows and we become wiser over time, just like the digital twin becomes wiser over time. The only difference is at the time of death. At the time of death, unfortunately, humans lose both, the body and the brain. In this case, you don't have to lose the brain. You can recycle the asset, but you can keep its digital twin and all that knowledge over decades to use it to know more about how to build the next one. Within that space, it's easy for me to define BIM, because I always get that question, what's the difference between BIM and digital twins? That's BIM. BIM is that little yellow line with as designed information, product information. And if you're lucky, you might also have a design status model that has your design phase process information, or your as-built BIM with your construction phase product information, or your project status model with the construction phase process information. All of these are static models that in many cases don't talk to each other. We've now seen some efforts where we're trying to put these together and create, let's say, a more holistic BIM, which is still a static model, but at least has all that information together. But what we haven't reached yet is this. That's the potential, the green space. See, the potential for digital twin is to have a dynamic model that has all the information about the answer since conception. And this is very important because the most valuable thing about digital twins is their ability to go back in time and forward in time. The ability to do forensics and understand why something failed, what decisions did I take 10 years ago that led to something failing now, but also predictions. If I continue in that same trajectory, what might happen 5, 10, 20 years from now? Or if I change that trajectory, what might be the answer? This is why we have to achieve that if we want to get the most value out of these systems. Now, some other very fundamental things. Digital twins are made out of information, not raw data. We don't want to blow up digital twins with unnecessary data. We want to process it and keep only what's important. We then want to enhance it with AI tools and convert the information into knowledge by getting your information patterns via interpolation, or the knowledge patterns via extrapolation to get the insight. All of these are perfect AI use cases, and this is why AI is very important to digital twins and vice versa. You need AI to develop digital twins into higher maturity, and you need digital twins to allow for AI to give you more information than you could before. Perhaps the most important slide I want to show you is this one. We already know what it takes to plan, design, construct, maintain, operate an existing physical asset, any one of those buildings out there. We don't know how to do the same thing for the digital asset. We have ways to plan a building. We don't have ways to plan the digital twin of that building, right? So if I am a big customer, I know how to procure a building like this one. I don't know how to procure the digital twin of it. I don't know what to ask for, right? How to understand the scope, the feasibility, the costs. Same for design, deriving the DT asset class, hospitals, roads, bridges, designing the data structures and cloud architectures. We don't have these in place yet. We have to do research for that. DT construction, how to populate that class and automatically derive a specific asset instance. In other words, how can I digitize this building and make a digital copy of it automatically? And then how to update it over time, that's maintenance at varying sampling rates per attribute. But most importantly, how to operate it. See, just like the physical twin, the first 4 are pure cost. The value comes out of the last one. And so the first 4, you want to minimize, optimize, get them done as cheap as possible, as reliably as possible. The last one is what gives me the value, and that's where I have to put in a lot of attention on. I added this literally 20 minutes ago. I know it's after lunch, so you're not hungry anymore, but I like the hamburger analogy. I've discussed it with a few people today, and I thought it was important to bring it on. We are now in a place where we have already a lot of data. There's a lot of data out there that is sitting in loads of different distributed databases. At the same time, we have a lot of authoring tools, the kind of tools that let us manipulate that data. But so far, the relationship between the two has been a complete vertical relationship. One database and one tool, one functionality and one set of data behind it. This is what I would call a sausage. I just couldn't find a good sausage picture to add here. Where I want us to go is to the hamburger model, where the entire bottom bun of that burger is the various databases that exist out there. The top is all the authoring tools that exist out there. And the nice bit of lettuce in the top and bottom there is your security layer. And the burger in the middle, that meat patty, is the indexing layer, the ability to glue everything together. That is something we don't have. That is what we need to build if we want to create good digital twins. It's that indexing layer that connects all the information. Having said that, I'll stop with the more theoretical discussion and I'll go into examples. And I'll present examples specifically from the digital twins construction phase, where we've done quite a lot of work. Let's define, first of all, construction. We're looking at a real asset, for example, a bridge or a building or any other asset. I want to automatically capture it and create its digital model. How do I do that? Well, I go there and I get my raw data, points, pixels, thermals, GPR, and other information. Once I have that, I automatically convert that to objects. And then I take those objects, I put the additional layers on top, the visuals, the thermals, everything else. And on those layers, on the combination of these layers, I start detecting additional information, condition information or other information. This is the use case. So how do we do that? Well, we've done a lot of work on every one of those steps. On step 1, on extracting raw geometry, long time ago, we came up with a method called mid-range mobile videogrammetry that leverages the fact that we have very strong lines and planes within infrastructure assets. And by doing that, we were able to reduce the spatial error down to a sub-centimeter error from 25 meters away. Now you can do that with a mobile phone. You can walk around, collect a video of a space, and use an app we've created that's commercialized in the US through a company called Pointivo that will do that conversion for you. Once you have the points, you can then equalize the densities, fix the holes, and produce a good point cloud. We've also built some tools more recently to help the person who's actually doing the scanning. This is our latest sensor that combines LiDAR, RGB, near-infrared, IMUs, and you can put additional cameras on that. We're able to synchronize those in space and time as you walk around on any site, either a finished site or a construction site like here. But not just simply sync them in space and time, but also predict the error in real time. And this is what you see here, real-time accuracy predictions. So as you walk around, you know how good or how bad the data is. And that allows you to change your scanning pattern so that you only leave the site when everything is green, when everything meets your accuracy specifications. That's what you see in this use case. As this person is walking around, he will then create a loop closure, go from green to red, and through that loop closure, the data can then be locally updated and fixed. He can do multiple of these loop closures, the rationale being that this will help him correct all the data, so he only leaves when everything is green. The next step is to take all that raw data and convert it to something usable, like objects. The problem with that is that that's actually a problem that's 10 times bigger, right? For every day of scanning, modelers spend about 10 days modeling. And even worse, we're looking at point clouds in many cases with over 30 billion points. We don't have a computer today that can open that file. So you have to process it piecewise and then stitch the results together. The worst of all is that it's a boring job. Imagine modeling pipe after pipe, valve after valve, wall after wall. This is not something for humans to do. This is clearly a case for automation. There's an example there that reactor building, 40 billion points. It took 10 people 6 months to make the model. How do we fix that? Well, we started a long time ago with very simple methods, detecting columns from a webcam and a laptop. 10 years later, now we have the ability to take the raw data from a bridge. We've scanned about 14 or 15 bridges, and we can automatically convert that into objects without any human involved, right? We're detecting the objects here. This is an AI application, and it's important to highlight we can do that for real objects. In a bridge, no pier is straight, no deck is straight. Every real component is not a cuboid, and we have to still be able to capture it. That means going from this, which is just points and pixels, to objects, and from objects to a model without any human intervention. Very quickly, we've done the same for buildings, using a similar strategy, which we called it the deep structure digital twin generation process. I know in the case of a building that it's a building, so I can use architectural priors and engineering priors to make some intelligent assumptions about it. It's a building, so it probably has floors. Job number one, segment the floors. Once I've segmented the floors, now let's segment the rooms inside a floor. Once I've segmented the rooms, I can then make, again, assumptions that there's probably a ceiling above me, there's a floor below me, there are walls around me, and so on and so on. This is a hierarchical decomposition process that allows us to go from the raw data to the rooms, to the floors and ceilings, onto detecting walls and spaces and fitting the components without any human involved in the loop. We can now do the same for industrial facilities, only with a much more of a deep learning approach to it, by detecting mechanical components, cylinders, elbows, flanges, I-beams, and other elements in a very bottom-up manner, but then using the connectivity of the mechanical system to detect the missing elements, create the relationships, and build the whole piping network. We're working here with BP, Aviva, and other companies to do that. We then go a step further, because it's not all about geometry. We want to enrich this geometric digital twin with additional information, such as condition information. And on that, we've done projects, again, on bridges, taking in all the textures of an actual digital twin of a bridge and detecting on those textures all the types of problems you see there in that list, measuring them and assigning those measurements as properties back to the model. We've done the same for roads. Simply driving forward, we can use your parking camera to capture the cracks, the patches, the potholes, all these other issues measure them, and assign those measurements back to the model. And this is actually something we've done a long time ago, and it's now commercialized widely. We work, for example, with Mercedes, who was already doing that full time with every one of their cars. This is an important message to everyone. In case you didn't know it, every pothole is monitored by Mercedes every day. Just keep that in mind for a moment. We've also brought sensors and sensor data back to the model so you can make decisions about those sensors. It's about bringing the time series data on your components and understanding what happens on your asset as you use it in real time. That's the point of a twin system, because you have to connect the loop between the physical back to the digital and back into decisions. The long-term target is what I call the national digital twin. I've worked a lot in the UK, initially with the Centre for Digital Build Britain, and now with several parts of government towards achieving those types of models for every single asset. That's what the UK wants to achieve. For every asset, we want to have at least basic digital twin that can help us manage the asset, and over time have the ability to enrich it and get more value out of it. There's already a lot of data out there. So for us, this is more of an integration challenge. How do you take the different layers of data and put them together and make the most sense out of them, using the hamburger model I was discussing earlier? One last bit I want to mention is about exploiting the digital twin, because what's the point of making it if I don't get value out of it? So let's talk about that value. I'll present some examples. The first one is through the design phase. This project is called Digitally Enabling the Design for Manufacture, Assembly, and Maintenance of Bridges. The use case behind it is HS2. I don't know if any one of you here has ever heard of HS2. It's the high-speed 2 rail line connecting London to Birmingham. That rail line has 300 bridges. What those 300 bridges have in common is that none of them are iconic. None of them are anything special. You want to build them on time, on budget, maximum certainty, minimum disruption. Perfect case for DfMA, perfect case for off-site manufacture. Except the delivery system in the UK is not built around off-site. It's built around bespoke. So how do we convert one to the other? Step one was trying to understand the process. And we went through the entire process from route alignment all the way to a delivered bridge. We mapped every single decision and the data you need to make that decision. And we linked them together. And this allowed us to do two things. First, to reorient these decisions so that I have the data that I need to make that decision at the time I need to make it. For example, bring in the choice of a crane very early on in the project, because based on the crane capacity, the weight of the components I design is limited. So I can design components that are fit for purpose for that crane. The second thing was, this allowed us to understand what are the dependent and the independent variables of the problem. And what this allowed us to do is, well, actually create a design automation solution. See, for the case of a highway overpass, you don't actually have that much flexibility. Highway overpasses are so extremely constrained by regulations that the actual control variables were only 16. So all we have to do then in this context, once we build a design automation tool, is have our design partner, Tony G, sit with High-Speed 2, ask them those 16 questions, put the numbers in, click the button, and here is a Pareto optimal of designs. This is a process that used to take them 7 weeks for one design. Now they can produce 100 in 2 minutes. Design automation will have a big impact on the design space as we move forward. It will change the sector quite a lot. On the construction phase, a very simple example. I have my digital twin, it's schedule loaded. I superimpose it with the physical twin with augmented reality or any other application. And by doing so, I can see the difference. All of these components were supposed to have been built at the time this video was taken. As you can see, many are not built. The project was behind schedule by 9 months. Now I can measure that automatically. And I can do a simple volumetric comparison, and anything that's behind schedule, I can automatically mark that back in the model. We can also bring that technology inside the offsite manufacturing facilities. So you have here a worker who's just consulted the BIM file, and he's about to build a rebar cage. As he goes around, he takes out his tape measure, he measures, he brings the bars in. We created a vision tracker that can capture him and follow him for the entire shift, 8 hours. So even if we see a little bit of him, we can still follow him. When he comes back, we can pick him up again, continue tracking to build that spaghetti diagram. We link the spaghetti diagram back to the digital twin model. And by doing that, we have component level productivity information. In addition to that, we noticed that this guy was spending 60% of his time understanding the model and measuring. Neither of the two are value-adding activities. So what we did instead is just bring the model right in front of him. If you bring the model in front of him, he can just build the components exactly where they are. And we can use augmented reality tools to measure the quality of his work in real time and gamify the process and give him rewards for doing a good job. We also went a step further in helping the worker by bringing in robotic teleoperation. I don't know how many of you have seen the movie Real Steel, where Hugh Jackman pretends to be the boxer, but it's actually the robot that does all the work. The first time I watched that movie, my thinking is, well, why a boxer? Why not a construction worker? Imagine how incredible it would be to have a worker like that. I don't need a crane anymore. I can just pick up a huge steel beam and carry it in my shoulder, right? You don't have the limitations of humans. But to do that, you need to actually solve the robotic teleoperation problem. How to go from the human to the robot and back to the human reliably. And we've done a very small demonstration of that, which is what you see here. A very simple project. And this is where I really love Cambridge students. This is one undergrad, 2 months. He wrote this code to capture fingers, hands, all the motions of the physical human, and then use that to have this virtual worker lay some bricks, pick up a spade, put some mortar, put another row of bricks, pick up a hammer, align the bricks and all that without ever having to touch any one of these components. For those of you who remember Kinect games like Kinect Sports, you can call this Kinect Bricklayer, right? It's something like that, but it shows the potential. Other examples of use is an obvious one, bringing digital twins into your space and comparing digital and physical, or exploring the digital twin in the office so you can see the actual problems and defects without having to visit the site. In augmented reality or in virtual reality, there's lots of virtual reality tools like that. If you ever come and visit us in Cambridge, we can put you into that device and you can walk around the bridge and see the issues. Another example I have here has to do with asset protection. Very interesting example. In the UK, a truck hits a bridge every 4 hours. Now, most of these hits are very minor. It's a truck that's too tall and just barely scrapes under a bridge and creates minor damage. But in some cases, it can be serious damage. And we were talking with London Underground. They were telling us that their top 10 most hit bridges get hit once a week. How do you protect these assets? The passive solutions don't work. The active solutions with the laser beam are too expensive. And London Underground was saying, I'm not paying that money. I'd rather let the trucks keep hitting. So we needed something that was cheap and can do the same job. So in this case, we replaced the laser beam with a camera much further upstream. The camera is mounted at the overhead plane. So the overhead plane becomes a line in the view. Anything above that line is an overhead vehicle moving. So we use that to detect that overhead vehicle. warn the driver. If they don't exit and they hit the bridge, we use accelerometers to capture the hit and record the video that was just captured a moment ago, because we capture the license plate through this way, and we can charge the offender. And you can see how this works over here on the Fairlope Station bridge, where we're able to capture again the overheight elements and get that person recorded properly. So in addition to these past projects, we're also doing a number of projects that are active right now. There's about 65 million pounds of ongoing activity in this space at Cambridge. CBIM is one of them, where we're working on generating geometry, enriching products, modeling processes and applications. BIM to Twin is another. How can I do construction, only this time with a digital twin? So you have a graph at the core, and it's the graph that informs every single aspect of that process. We've reimagined that process as a result of having that graph in the middle. The same for roads, and this is the unfortunately named Omicron project. And we came up with that acronym before the variant came about. So again, in this space, we're looking at the loop I presented to you earlier: inspection, data into the digital twin, decision support, back into intervention, and inspection again. And you can see here some of the work we did on designing the digital twin and how that fits within that interface. Also in collecting the data, using our PointPix sensor mounted in the back of a car and measuring how fast and how effectively we can work with that sensor. A more recent project is trying to apply this technology on dams. So we're now working with Hydroflex to create the digital twin of a dam and the facility that produces power as a result of the dam, and how try to digitize the whole process for them. And also how to allow human interaction versus using what we call the chat twin, using ChatGPT enabled on the digital twin so that humans can much more easily interact and extract data out of it. The use case I want to focus on the most, though, is this one. It was mentioned before in the introduction that one of the projects we have on Cambridge is called the Digital Roads of the Future Initiative. And in that initiative, we're looking at assets as a combination of product and process, and physical and digital. And we're trying to do significant advancements across the quadrants, but also on the arrows that connect them. For example, under physical product, we're looking at how can we take the existing inert materials and convert them into smart materials, aware of their state and properties, assisting their maintainers and users. Under the physical process, we're looking at how to automate construction, maintenance, other operations. Under the digital product, it's the things I was discussing earlier, how to plan, design, construct, operate, maintain digital twins. And under the digital process, how can we get data out of the smart materials through the robotics into the digital twin, connected with everything else, and then leverage all of that to drive decisions and insight to inform design, construction, maintenance, and operations. Within that space, this program is now grown to about 17 million pounds, and it keeps growing because we get new partners all the time. And it's made out of initially 2 grants, Digital and Future Roads, and now it's expanding into an alliance similar to the Hong Kong's CIC. We have the Roads Research Alliance in this context. These are the original partners of this alliance, and we have, again, companies joining all the time. And what we're doing with that group is we've put together quite a lot of people, a lot of researchers, fellows, and others to help us solve these challenges. And I have here my favorite Cinderella slides. I see you smiling. I brought them in because we discussed them earlier to explain why. Why do we need to solve this problem? The context here is I was watching Cinderella together with my young daughter the day before I had to make a presentation. So I was working on the presentation in my head while watching the movie, and everything in the movie clicked. It was exactly what I wanted to present. So the use case is Cinderella is roads in our context. Anyone know Cinderella's sisters, their names? No one? Have you ever watched the movie? So we have Anastasia and Drizella. Anastasia is mass transit. Drizella is autonomous vehicles. And let me explain why. Roads carry over 80% of all passenger miles and domestic freight, but only receive about, 15% of the investment. So they do most of the work like Cinderella and are significantly underpaid. All the money goes on to the older sister, Anastasia, which is rail and mass transit. And for the younger sister, this is a slide I've taken out of Mercedes. As you very well know, the car industry has gone from a mechanical industry 30 years ago to be now a bunch of data companies, right? All the cars are now sensors on wheels. That's not the case for our infrastructure. We have created a huge technology gap between what drives on the road and what happens in the road. You can see here what Mercedes is producing every day. Within that space, roads are not fit for purpose for future autonomous cars. We have a big gap and we need to close that. And we need to drive more investment into the infrastructure side to make that possible. And to do that, we need a fairy godmother, going back to Cinderella. And the fairy godmother for our sector is the alliancing model. See, the big difference with other sectors, I picked here Microsoft. Microsoft invests every year $2.5 billion in R&D. That's more than the entire UK construction sector invests in R&D combined. If you go by market cap, if Microsoft was a human, the largest privately held contractor in the UK is Lengorug. The difference in market cap is about 1,000. So if Microsoft was a human looking down at Lengorug, they wouldn't even be able to see Lengorug. It doesn't exist, right? So this industry is an industry full of little ants. And the only way for ants to survive is if they work together. That's the message and the reason for alliancing. So last Cinderella slide from that deck is, this is exactly why we need to work together and go to funders and ask for the glass slipper. Okay? So that's the last Cinderella slide. Moving on. So the Roads Research Alliance was put together for that purpose. And we are working alongside all of these partners to make that possible. One of our projects is Digital Roads, where we are working together with the car sector to enable this loop that you see here. So imagine Mercedes over there on the right, the autonomous car, able to give us all the pothole data, crack data, everything they detect from the road. We take that into the cloud. We are building that cloud to allow us to process that information coming in from the car and drive it into decisions. Is it a big pothole? Do I need to fix it right now? Is it a small crack? I can fix it next year. And based on that answer, if it's a simple problem, send an autonomous maintenance vehicle to fix it, like a crack or paint a new lane marking. But if it's a more serious problem, send that to humans and let the humans worry about that decision. Within that space, we are working with building those two components, the cloud and the autonomous maintenance vehicle. Now, rushing towards the end, the Roads Research Alliance aspires to become an institute, and we've been working along with our partners to achieve that goal. There's a lot of activity in that space. If you're interested, please catch me afterwards. I can tell you what's happening. And I think I should close at this point. Just a little plug for my book on infrastructure computer vision, to thank all the people who've done the work. There's just a few of them down there and a few of the sponsors up there, and say thank you.
Okay, now I'd like to invite Professor Ding Xiaoli and also Professor Zhang Yuhong, Wang Yuhong, sorry, to be the panel member who will manage the discussion.
Yeah, I want to thank Professor BRILAKIS for the very interesting and inspiring talk. I think we have learned a lot from the presentation. It's my pleasure, and also Professor Wang, we actually facilitate this Q&A session. I think we have questions maybe from the site and also from online. So we need to look at both. So do we have any questions from the side here? Yeah, there's one from the back. Yeah, you can use that.
Hello, thank you so much for the presentation. It's very inspiring. And I just have a question about the scope of the digital twinning. So for example, for the buildings, maybe the infrastructure or the systems are more complex than bridges or roads, I mean, other infrastructures. And so probably they have higher requirements about the accuracy or precision of the detection or the scanning. So how does it work? I mean, the digital twinning for the buildings, I mean, the building systems or building trees, for example, all the paths or the lines, like maybe hidden from all the surface. Yeah.
Thank you. That's a very good question. You are correct. In the case of bridges, everything is exposed. Whereas in the case of buildings, many components are hidden and you can only partially see them or maybe even not see them at all. Well, if you don't see them at all and you have no other information, the best that you can do is you can infer them. You can assume of their location. And maybe you're right and maybe you're wrong. You can never be 100% right. This is where the AI tools that we use help us achieve that. For example, with mechanical elements that you don't see, we know that mechanical elements are still a connected system. And so if you can see part of the system, but there is a couple of pipes or elbows that are missing there, because you know that it's a connected system, you can infer that connectivity and make your best guess of what might be there. That's what you can do without doing an invasive process of removing components to actually see what's there. And to be honest, from what we've tested so far, it works quite well. 80% of the time, you've made the right assumption of what actually is there. But the only way to be 100% right is you have to open it up.
Thank you.
Yeah, can I suggest we have a question from online first? Professor Wang, can you read this long question from online?
Thank you, Professor Ding.
Yeah.
But we do have quite a few questions from online audience. I will read the second question because the first is irrelevant. So the second question is, Professor BRILAKIS, I would like to hear your views on the way forward for construction technologies. Building information modeling software can help us design and construct a building, while digital twin technology can help us maintain and operate that building. The former helps visualize the design and the construction of assets, while the latter enables virtual interaction with the assets. So the first question is, what are the strengths and the limitations of each technique? Second, what can be done or achieved by BIM, but not digital twin? If no, does this imply a shift to a digital twin is needed for the sector? Third question, in developing digital twin technologies, what are some major bottlenecks so far?
All right, thank you for the question. So one of the reasons I spend a lot of time trying to explain digital twins as a definition and particularly that slide I used to compare the difference with BIM, is to explain to people that actually BIM is a digital twin. It's just a really basic one. Drawings from 50 years ago on paper are a digital twin. It's just an even more basic one, right? All we've done, this is not a revolution. This is an evolution. Over time, we have evolved to do more and more and more. So are there any disadvantages to newer systems compared to the older ones? Perhaps there are in terms of simplicity. Complexity is growing up, as I mentioned in my slides. But if we want to manage assets, this is unavoidable. What we have to do to manage complexity is to do a much better job at encapsulating complexity. And on that, I want to highlight an example. I visited Larsen Toubro's headquarters in Chennai a few years back, and they had me visit their largest building on campus, which was a huge BIM training facility, full of classrooms teaching BIM all the time. And they were absolutely convinced from the vendors that this was the only way forward. The only way forward is we just have to do a lot of BIM teaching. They never stopped to think that maybe one of the reasons that we have to teach so much BIM is because the software is crap. Right? We're talking about software that's still built on a foundation from the 1990s, where even to install the software, you need to be trained. And I want you to contrast that for a moment, and this applies to the second half of the question that was asked by the audience member about the barriers. I want to ask you for a moment to compare that with, let's say, mobile phones. The example I like to bring is that when my daughter was 1 year old, she was able to unlock my phone and fire her Peppa Pig app and start playing. So she doesn't even need to know how to read to get value out of a very complex device like a smartphone. BIM is not as complex, and yet I would have a hard time using it today, right? So that means we have a lot more to go on encapsulating complexity and getting the most value. And to me, that's the biggest barrier.
Thank you.
Yeah, maybe I have one from the side.
Thank you. We are now trying to do some digital twin system. And as you said, I found what you the key issue is not about having a digital twin, but twinning. And we found that the bottleneck is infrastructure and how to turn the built environment into the physical twin. Because the infrastructure and we get the sensors to capture the data and the data, how the data is transferred into to the database. This it involves cost. So this is how many of the ideas cannot be done. Do you have any of these solution or this interaction result of this, how the cost and infrastructure, the cost can be brought down and infrastructure is upgraded.
So you're perfectly right to say that collecting data costs money, cleaning the data costs money, curating the data costs money, processing the data costs money, all of that costs money. But just like the physical twin, there are costs associated with the digital twin. And perhaps the better way to look at it is that nothing is for free. There is no free lunch. But the question is not whether it's free or not. We know it's not. The question is whether it's affordable or not, or whether we're paying a good price for it. And this is where I invite you to start comparing digital twin costs with physical twin costs. I will give you one such example. We've done the costing for making the digital twin of the corridor from London to Cambridge. That's M11 from the junction with M25 all the way to Cambridge. That's 60 miles of road. And we got the cost to be £750,000. That's about £12,500 per mile. That's the cost of the digital twin. What is the cost of the physical twin? The cost of the physical twin is 50 million per mile. If you divide £12,500 to 50 million, you will see that the digital twin costs 0.00 something percent of the physical twin. So the argument we are making to national highways is that next year, if you build one less road, you will have enough money to digitize the whole country. So that's the way to make your argument.
Thank you.
Yeah, maybe we get another question from the side.
Okay, thank you, Professor. I'm interested in your the hamburger theory about the DT. I'm interested in the bottom layer of the hamburger, the bread one. So building a DT is a complicated project that may sometimes involves different stakeholders and the vendors to contribute different types of data. So do you have any suggestions to motivate these different stakeholders to contribute to the DT, because most of them in our practice, they are reluctant to provide this data. So how can incentive them to contribute to it using money or policy or some education extra? So I want to have your suggestion or insights. Thank you.
Very good question. Thank you. I would say the answer lies from understanding the supply chains. I'll take one example of a supply chain and apply that rationale. So going back to the roads example, which we've used quite a lot. In the UK, there's only one client, National Highways. That's the Strategic Road Network client. So if you can convince that one client to get on board and put the data in your system, every one of their 3,000 suppliers is going to come on board, because it's a monopoly, right? And you have to understand how that ecosystem works. Now, is that an easy thing to do? No. So probably you start the other way around. You work with a few companies and get them to put some of their data on board to prove the case as a pilot to government. Then you go back to government once you've proved that case and get them to put their data on board. And once you've done that, everyone else by necessity has to follow. Now, that's not so easy to do in a more distributed supply chain. For example, buildings where you have multiple clients. So you cannot enforce that monopoly power of a single client to make that possible. But if you can prove your case in one sector, it's fairly easy to imagine how other sectors will get this fear of missing out, FOMO, and start thinking about implementing it themselves. You don't need to win everyone. You just need to win a few.
Okay, thank you.
Can we bother Professor want to read another online question?
We'll pick
Yeah, maybe we'll read
online, right?
Yeah.
Another online,
Yeah.
sorry. So our online question is, do you have any problem of finding the appropriate and reliable sensors for collecting all types of data and from all types of physical devices? Another problem is the life of the sensors.
Okay, both very good questions. Shopping around for the correct hardware is always a challenge, and that's because the information is never quite straightforward. You have to do a very, very in-depth comparison and then effectively shopping analysis to see whether I should buy this scanner or that scanner or one sensor or another sensor. But it is a fairly straightforward problem. You just have to put some effort into it. And the good news is that there are many academic groups that publish these comparisons these days. So you can look them up online and get some of these comparisons. Sorry, I forgot the second part of the question.
Any problem with the lifespan of the sensors?
I mentioned that earlier. Everything that is technology these days has a diminishingly small life cycle. The pace of innovation is very fast and is accelerating. So even if you buy something today that can last 5 or 10 years at most, it will become technologically outdated much faster than it stops working. And this is where we're looking at perhaps renting devices. The same thing happens with construction equipment. Large construction excavators, rental has become very common, exactly because you want to always leverage the latest technologies. And that's the way to get it.
Thank you.
Okay, maybe we have the gentleman in the back. Yeah.
Professor BRILAKIS, thank you for your talk. Actually, this is my second time to listen to your talk. One is, from the Zoom, and we are the friend, for LinkedIn. And thank you, you send your presentation to me also. Actually, I would like to ask is, okay, we are talking about digital twin and all the technology, but one thing I think is very important is about the people. Because as you know, in your last slide, we need really, a network of people to join, the digital twin worlds. So actually, when we go into a single project, I think the engagement of the people, is very important. And I will see, in today, we still need of the people to engagement, such as, when we do the BIM, just in a simple BIM modeling for design and construction. We are very difficult enough to have all the stakeholders to involve on that. And the second point is, okay, as you mentioned, okay, digital, the value of the digital is, on the operation and maintenance. So how about today for the FM people, the facility and operation people? It seems they are still far away from the digital worlds. So what do you think about that? So how we can speed up the engagement of the people to first to build up the digital twin? Thank you.
Thank you. Very good question. The example I like to bring to answer that question is construction workers. Construction workers also hate BIM. They prefer to use drawings. Well, actually, they're doing that because they're smart, not because they're stupid. When you're on site, drawings are the best thing you can have. Why? Because drawings can be huge, right? A lot of big space, which is very good for visualization. You can get them dirty. You can tear them apart. You can just print another, right? There are practical value on site to use paper. And also, BIM, we talked about the quality of the software before. It's just too damn difficult to use sometimes, and you can get that value out of the drawing a lot faster. This is reality. So I don't blame them at all. We have to keep in mind that those same construction workers are just as addicted to their mobile phones like the rest of us. So if the mobile phone addiction of every person on the planet is like heroin, BIM software isn't even a cigarette. And this is the real problem we have to fix. We can't just simply force people into using the tools. We have to make those tools a bit more attractive to humans.
Maybe Professor Win.
Okay, Professor BRILAKIS, thank you very much for your lecture, and thank you for sharing your work and your life in UK and in the US. I enjoy it very much. I have two small questions. So the first question is that you talk about a lot of things about data collections, sensors, and all this in the DT. I wonder what is your viewpoint about the artificial intelligence AI development going to change the digital twin infrastructure? This is my first question. Secondly, so what is your viewpoint since you work in both UK and the USA? And so what do you think the difference between these two countries in terms of their emphasis on the DT technologies in the construction infrastructure?
Thank you for both of the questions. I'll start with the second one. I think the major difference between the two countries is not the individuals that are amazing academics on both sides of the pond. I think it's more the financial structure behind the funding agencies that pay for that work and make it possible. So the UK has a much bigger emphasis on large grants, and you have many large projects in the UK that focus on this, and also a much bigger emphasis on collaborative grants with industry. So just about every project I have is co-sponsored by companies. That's not the case in the US, especially with National Science Foundation projects. You don't have to have hard cash from industry. And there isn't that culture anyway. The outcome of that is you can generally not do large concentrated development efforts, R&D in the US, certainly not in universities. And this is not just for digital twins, I would say it's for many aspects of construction and industries like that. On to your first question, remind me one more time the first question, sorry.
How do you think the development of artificial intelligence,
Yes,
AI, going to change
Yeah.
the digital twin infrastructure?
I mean, AI is, as you saw in my slides, the key that makes this possible. It's what allows us to connect all of this information together, because we have way too much information, and it is not possible to treat information the same way we used to with relational databases. We have to, even running queries is something that has to happen with AI these days to process the data. So I cannot imagine digital twins being functional in the future without amazing AI tools that help us convert data to information, information to knowledge, and knowledge to insight.
Yeah, can we get the gentleman in the back?
Hey, thank you. So I would like to ask questions about when we're doing a construction project, in addition to the digital twin, and we also need to consider costs and also need to consider time. So, and in how, like it with this regarded, how are we going to build such knowledge into digital twinning? So that's one side of the question. By looking at the other side, because when we're doing a building and there are some precious equipment like cane that actually play as a resource role, but not necessarily in the model itself. So how would you model those kind of dynamic requirement? Because of, in order for the construction panel to hang it up to the top of the roof, that you need that crane to design, to schedule. How would you doing that? Because in Hong Kong, in the case of MIC, right, when the MIC is being done in China, we need to ship it back to Hong Kong. And in Hong Kong, we don't have enough space for the MIC to store. So therefore, as soon as they come in, they need to be put it right away. Those are the scheduling and the processing problem that we need to handle. Any suggestion that you can help us to think about this issue?
So if I was to go back to the hamburger example I presented, a lot of these applications would be at the top bun, basically the authoring tools that help us schedule, plan supply chains, and so on. How these tools work, I think that's purely a job for the private sector. But to enable the private sector, you need to have the data layer in the back that makes all that data accessible across the board. And one of my motivations to be here in Hong Kong with you today is to give a strong message to the Hong Kong government that just like we build roads to incentivize the economy and allow businesses to thrive by offering mobility, we need to build the equivalent digital roads, the digital infrastructure to allow for businesses to create applications that service, for example, what you mentioned, to address these kinds of problems. And we don't have that right now. And we cannot even build those solutions because the only way to build them is to have our own separate data pools, which are not connected to anything else, and therefore cannot actually address the problem you mentioned. So that's a really good use case for the hamburger example. Thank you.
Yeah, can we invite
Okay.
Professor Wang to
Yes,
read a couple
Thank
of
you.
questions?
So we have another question. Thanks, Professor Ioannis, for the amazing sharing. May I ask what's the difference between the words digital twinning and the digital twin?
Well, one is the noun, the other is the verb. The twin is the not physical, the digital dynamic model with the graphs and indexing structures that make it possible to connect data and provide it to authoring tools. It's the hamburger. Twinning is all the processes that relate to designing that hamburger, constructing it, operating it, and maintaining it. And you need to do both.
Thank you.
Maybe get another one.
Another one?
Mhm.
Okay. Battery of AR or XR is not enough to use for a long time. Maybe it will be solved soon. So what do you think the roles of AR in the digital twins?
There are multiple uses for augmented reality. One of the uses I have found as a really, really good use is for communicating with construction workers or in any other environment where you have people who don't necessarily speak the same language. Construction workers is such example because in most countries, the workers don't speak the same language amongst themselves or with their supervisors. Take an example, the US, where the workforce primarily speaks Spanish, the UK, where the workforce speaks Belarusian or other languages, or India. India has a huge communication problem because most workers don't speak Hindi. They speak the local dialect. Having AR tools that can simulate to them exactly how work needs to be performed reduces situations where you might have construction mistakes.
Thank you.
Yeah.
Thank you, Professor BRILAKIS, for the very interesting and inspiring talk. I just have a small question. Since I think using the digital twin technique can model the whole building environment from the relatively large scale. And according to the case study that you present, you use the 3D scanner to detect the changes in the bridge and some single infrastructure. So I wonder if we want to apply this technique to the whole city level, even if we combine some like airborne radar, does that mean it will sacrifice some spatial resolution? Thank you.
I think you need to pick the resolution that's appropriate to your use case or to the envelope of the use cases that you have in mind. And so, like I said, we don't build the systems for just one reason. That's the sausage, not the hamburger, right? We want to build them for a variety of use reasons, and you have to pick the most restrictive use case in terms of what's the right resolution or error. We have these days the hardware to get pretty much whatever you need. That's not the problem. The question is similar to the question that was asked earlier about the costs. And these things cost money. If you scale it to the city scale, they cost a lot of money. But if you consider the value of the twin versus the value of the physical asset, it's actually nothing in comparison versus the value that it has. And one example of value, I was told by National Highways in the UK, they value their data set for more money than the physical infrastructure. Just keep that in mind for a moment. They value their data as more expensive than the entire value of the strategic road network in the UK.
Yeah, we still have a lot of questions online and also on site, but we have spent quite a bit of time already. So can I suggest maybe we have the last on-site question and also one more online question?
Okay.
Yeah, maybe we we give this to that gentleman first.
Okay, thanks for your amazing talk. So so when we talk about digital twin, under most of scenarios, we only consider ground-related buildings, on the ground or underground. So my question is, could you share some visions and insights about the digital twin ocean or underwater digital twin?
I'm afraid I don't have an example to share. I know that anything that is either underground or underwater, when it comes to this space, is at least a good 10 years behind. I work with a lot of geotechnics colleagues, and this is what they tell me, that when it comes to digital twinning of the underground or undersea, we are at least 10 years behind. So there's a lot more research to be done there. We probably don't even have the right sensors to capture the data necessary to map the underground and the underwater correctly. And I don't have a clear answer for you, but it's an even more interesting problem, exactly because we're even further behind when it comes to addressing it.
Yeah, can we bother Professor want to
Okay.
read the last online question?
Sorry, the last one will be a long question. Okay. We are trying to automate the creation of a digital twin of a building MEP system, mechanical, electrical, plumbing system, by integrating BIM models and the building management system, BMS, which collect and store real-time operational time series data. However, the data mapping, i.e. link and visualize the time series data in the BIM model is time and labor consuming, sometimes relying on the third-party development tool like Unit. It is not beneficial to the digitalization of the construction industry. So what's the possible technological solution within the construction industry to this data mapping issue?
I hope I understand the question right. If I can broaden it up a bit into human information interaction, which I think this question alludes to, we generally have a huge problem there of how we best interact with these kinds of systems, because we are increasing the complexity fast and humans cannot process it. The example that pops to mind is the National Digital Twin of Singapore, where many studies showed that anyone above the age of 55 could not use it. We also have to consider the different needs of different people. Senior people have perhaps less tolerance for technology, and the things have to be much more accessible to them if they are to use it. Different individuals, minorities, others have different needs out of the systems, and we have to explore that space just as much as we explore technology. But usually this is what happens. You start first with the engineering side, where only the engineers can actually use it, read it, process it. And then eventually you understand that if you are to popularize it and get it to the general public, you have to bring the rest of the people along with you. And that involves a lot of research into human information interaction within the context. We haven't done it yet. There's a lot to be done. So those of you who are research-oriented students, that's an amazing space to work in.
Thank you.
Okay, I think I'm really sorry that we cannot handle too many more questions. We have to stop somewhere. I wanted to thank all the questions and also thank Professor Bilas for answering all the questions. I think it has been a very enjoyable session. Thank you very much.
I also want to thank everyone, including the all the people who ask questions, and no matter where you are online or from here, as well as all the participants for attending this session. I think it's very successful. I see the peak time of join number online is over 300, and we have nearly 100 people on site. So I think we have probably tens of thousands through the crowd. It's a very successful lecture. Congratulations. Thank you very much. And this lecture is adjourned.